Alright, in this next exercise, we are going to, again, find the set of all points that are equidistant from two starting points, or two given points. And we're going to think of those 2 points as the endpoints of a segment. So again, we're going to go ahead and put in our axes. I'm going to draw our y-axis. My paper is, again, landscape style. Works out pretty well. You don't have to be super duper precise about exactly where your axes go. They'll be fine. So, there we go. Okay. So our first point is A, and that is the point 1, 1. And then B is 3, 5. So let's see, 1, 2, 3, 1, 2, 3, 4, 5. Here's B. And then the point we're given to test is 6, 1. That's C. 1, 2, 3, 4, 5, 6, 1. Okay. And that is, one second here. Why is that doing that? Pause. Okay, here's point C, 6, 1. And we're supposed to show that point C is the same distance from B as it is from A. So, well, from A, that's pretty obvious. That's 1, 2, 3, 4, 5 spaces. You just count spaces. 5. To C, well, let's see. That's going to be up 1, 2, 3, 4, and over 1, 2, 3. So using our Pythagorean theorem, that's 3 squared plus 4 squared equals C squared. So there's a little pinch here. And of course, we've seen this before. 3 squared is 9, 4 squared is 16. That's 25 equals C squared, or 5 equals C. So this distance is also 5. So C is equidistant from B and A. It's the same distance to B as it is to A. Equidistant. Now we're trying to find all the rest of the points that are equidistant from A and B. As you recall, in our last exercise, all those points formed a straight line, and they cut the distance from A to B right in half. That segment cut it in half at a right angle. So, one of the things we'll look for is what's the halfway point between A and B. You'll notice A is over 1, 2, up 1, 2, 3, 4 to get to B. So over 2, up 4, we're going to cut that in half, over 1, up 2. Okay. And so there's one of our points. This is going to be halfway through, right? And then notice we've got to draw a line here. It's down 2 over 1, 2, 3, 4 to get to C. And down 2 over 4, we can kind of break that down into down 1 over 2. That point would be on that line, so we're just kind of drawing this line out. So it's this pattern, down 1 over 2, down 1 over 2, down 1 over 2. There's another point on the line. Going backwards, it's going to be back 2 and up 1, back 2 and up 1, back 2 and up 1. And I kind of like to draw a lot of these points out, because you lay your ruler out against, say 2 points that are real close together, and then if things don't go well, you can end up with like a big error. So I want to draw a ruler or a line far across paper as you can. So let's see, down 2 over 1, down 2 over 1, looking good. Okay. And I'm going to connect all of these points with a nice straight line as best we can. Okay. And all of these points should be the same distance from A as they are from B. And let's kind of test it out with a couple of them, okay? So let's pick this one here. This point here. Let's see. That's over 3, down 1. So that would be 3 squared plus 1 squared is C squared. 9, 10, 10 equals C squared. Square root of 10 equals C. So this is the square root of 10. You notice this is that same down 3 over 1 pattern, so we'll end up with the same thing here. Right there. Let's see, if we went back up to this point here, we'd have the same 1, 2, 3, 4, 5 versus over 3 up 4 pattern we had over here. Well, let's try something a little further out. How about this point way out here? Okay, so let's go. Okay. If I get my ruler in here, it'd be a little better, but okay. Alright, so this is up 1 over 1, 2, 3, 4, 5, 6, 7. So that's going to be 7 squared plus 1 squared equals c squared. That's 49 plus 1. That's 50 equals c squared. So that's the square root of 50 equals c. So this distance right here is the square root of 50, which is a number just a little bit bigger than 7. Down here we have a totally different a and b for our Pythagorean theorem. Let's take a look at it. It's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So now we've got, let's see, 5 squared plus 5 squared is c squared. That's 25 plus 25. Hey, it's 50. So square root of 50 on this one as well. So it works out. Now, of course, we haven't checked every single point on the line, but we've checked a couple. It seems to pan out that the points on this line are the same, all the same distance from A as they are from B. And also notice, we connect these, that this line does cut segment AB in half, and that's pretty clear. Over 1 up 2, over 1 up 2, right? And it looks like that's a right angle. A little question mark there. Not 100% sure of that yet because we don't know how to test that, but it looks like it is. Okay. All right, so now I want you to go ahead and test this out on your own. So let's go down here. You're going to look at point D. That's -8, -7. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. This would be point D. Okay. E is -4, 1. 1, 2, 3, 4, and down 1. That's E. Okay. And F is point -3, 6. 1, 2, 3. 1, 2, 3, 4, 5, 6. This is point F right here. Okay. So what we're trying to do is first we're going to check to see that from D to F is the same distance as from E to F. And then we need to find the remaining points that are also the same distance from D as they are from E, and we're going to use the same process as before. I'd pick the midpoint next, and I would use the down and over pattern, or the slope essentially, between the midpoint and F to sort of plot some more points along the way. There'll be a line that kind of cuts through like this. Then I want you to check, say, 3 more points on the line somewhere to show that they are all the same distance from D as they are from E. Oh, you know what? We also want the equation of the line up here. This one's pretty straightforward. Let's see. The slope is down 2 over 1. That's y equals -1/2 x, and our y-intercept 1, 2, 3, 4 plus 4. Yeah, we do want to have the equation of that line because we're going to need that for later. All right, have at it. Good luck.